Welcome back to the Explainer. Today we're jumping straight into the foundational elements of data organization. We're going to be diving deep into the architecture of relational databases, and we're drawing all of this directly from Alan Beaulieu's insanely thorough guide on learning SQL. I actually like to think of building a database a lot like constructing a house. You definitely don't just dump a pile of bricks on an empty lot and hope a living room suddenly appears, right? You need a rock-solid blueprint, you need specific building materials, and you need very strict codes and house rules to make sure the roof doesn't cave in on you. Well, in the digital world, those bricks and rules are your SQL schema statements, your data types, and your constraints. So grab your hard hats and let's get into this construction process.
To really understand why we need all this rigid structure in the first place, just ask yourself this. What actually happens when you try to insert a text string into a field that's meant for a phone number or an account balance? Without rules, it's literally total chaos. You'd end up with a database filled with mismatched, completely unsearchable garbage. Relational databases, and specifically SQL tables, are basically designed to bring absolute order to that chaos. By enforcing really strict constraints right from the very beginning, a database ensures your data stays clean, reliable, and ready to be queried at a moment's notice. So, here is our roadmap for today's Explainer. First, we'll decode MySQL data types. Then, we'll design your first table. After that, we'll look at populating and modifying data, see what happens when good statements go bad, and finally, we'll meet the bank schema. Let's get to it.
Starting off with Part 1, Decoding MySQL Data Types.
Okay, before we can even think about pouring the concrete for our database foundation, we really need to understand our building materials. In SQL, these are our data types. Every single column in a database table has to be assigned a specific data type, which dictates exactly what kind of information is allowed to live in that column. And it's pretty amazing how specific we can get with just text and numbers. For character data, we've got two main players. There's char, which is fixed-length, blank-padded string data, perfect for something super uniform like a two-letter state abbreviation. But then you have var, ch, which is variable length. It adapts to the size of the text, so it's a game changer for something totally unpredictable like a person's first name. Now moving over to numeric data, precision is everything. You might just need a tiny int if you're making a simple small counter. But what if you are storing positional data for a high-precision circuit board drill machine? The source actually points out that this kind of manufacturing data often requires accuracy down to 8 decimal points. No way you can use a tiny int for that. You need the exact right numeric type, like a double or a big int, just to ensure that drill doesn't completely ruin the board.
Now, time is rarely simple, right? And MySQL offers several temporal data types depending on the level of granularity you actually need. Let's say you're recording an employee's birth date. The date type, which just tracks the year, month, and day, is absolutely perfect. It is completely unnecessary to know the exact millisecond someone was born for payroll purposes. But contrast that with a package shipment record or, say, a bank transaction. For those, you absolutely need the date time or timestamp types. Those track the event down to the exact second. Choosing the right temporal type doesn't just save you storage space, it ensures your data is actually telling the right story.
Moving right along to Section 2, Designing Your First Table. We've got our materials sorted out, now it's time to actually pour the foundation. Because building a table isn't just about throwing code at a screen. It's a highly structured 3-step process that's explicitly outlined in our source text. Step 1 is design. This is basically the brainstorming phase. Let's say we want to track a person and their favorite foods. We list out exactly what we need: name, gender, birth date, address, and obviously the foods themselves. Step 2 is refinement. This is where we take those specific data types we just talked about and assign them to our brainstormed list. And finally, step 3 is building the SQL schema statements. This is the cool part where we translate our refined blueprint into the actual language the database understands.
So here's the anatomy of a create table statement for our person table in action. And notice how it almost reads conversationally once you get the hang of the syntax. We define our column names first: first name, last name, gender. Then we pair them up with our data types. The really crucial point here is that gender column. Notice we didn't just use a standard character type. The source explicitly highlights the use of the enum data type here. By defining it as enum mf, we are strictly restricting the allowable inputs to just those 2 exact characters. Nothing else gets in. Finally, we lock the whole table down with a primary key on the person ID. This ensures that every single person in this table has a completely unique identifier. Boom, our foundation is set.
All right, on to Section 3, Populating and Modifying Data.
The house is built, but, well, an empty house isn't very useful, is it? It's time to move the furniture in. To put data into a table, we use the insert statement. And there are three main components you have to give the database here. First, the table name. Where is this data actually going? Second, the target column names. Which specific rooms in the house are we putting this furniture into? And third, the actual values to populate. For example, the source walks us through inserting a record for a man named William Turner. We specify the person table, we target the name, gender, and birth date columns, and then we pass in the values, William, Turner, M, and his birth date. And just like that, our database officially has its very first resident. But what happens when someone needs to move out? The source uses this really great example where William and another resident, Susan, aren't exactly getting along. So Susan gets the boot, courtesy of the delete statement. Now, saying delete from person where person ID equals 2 is a surgical removal. It specifically targets Susan and removes only her record. But, and this is a massive, massive warning here, if you forget that where clause and you just type delete from person, that is a catastrophic mistake. You will literally evict everyone. You'll delete every single row in the entire table. So always, always double check your where clauses. Which brings us to section 4, when good statements go bad.
Look, mistakes definitely happen, but a well-designed database has constraints that act as locks on the doors. You kind of have to embrace the error. If you spend any time at all working with MySQL, you are for sure going to see text like this pop up on your terminal. Error 1062, duplicate entry for key primary. So what actually happened here? Well, our sources explains that this error triggers when you try to bypass the auto-increment feature and manually insert a primary key that already exists in the system. Remember, the primary key is our unique identifier. If person number 1 already exists, the database throws up a brick wall and flat out refuses to let you create a second person, number 1. The house rules are being enforced.
Okay, here's another beautiful terminal error for you. Error 1452. This one's a little bit wordier. It's complaining that a foreign key constraint fails. In the context of our source material, this happened when someone attempted to add lasagna as a favorite food into our favorite_food table, but they tried to link it to a person with the ID of 999. Do you see the problem? Person 999 doesn't actually exist in our main person table. The database is essentially yelling at you, hey, I can't assign a favorite food to a ghost.
To really demystify that last error, let's look at the actual definition of a foreign key constraint. All it does is ensure that all values entered into a child table, which in this case is our favorite foods table, must absolutely exist in the parent table, the person table. You simply cannot have a dependent record floating around out there without a parent record to attach itself to. This is literally the ultimate tool for protecting data integrity. It totally prevents orphan data and ensures that the relationships between your different tables remain logically sound.
One last error for the road. Error 1265, data truncated for column gender. This right here is a column value violation. Remember back in step 2 when we proudly set up our enum data type for the gender column to strictly only accept M or F? Well, if a user mistakenly attempts to update a person's gender to the letter Z, the database immediately rejects it. And it doesn't matter if it was just a typo or a malicious attempt to corrupt your data, the schema acts like a bouncer, making sure only the expected data types get past the velvet rope. And finally, section 5, meet the bank schema. So far, we've really just been looking at a very simple, isolated house. Let's zoom out to a fully finished neighborhood now. The source material introduces a comprehensive bank schema, and this is going to serve as our main playground for all our complex SQL learning moving forward. Think about this interconnected web of tables. We have an account table, a customer table, transaction, branch, and product. Think about how all of these relate to each other. A customer opens an account at a specific branch for a specific product type, and then they generate hundreds of transactions. The constraints and the keys holding all these tables together are vast, sure, but they follow the exact same foundational rules we just learned with our simple person table. And that leaves us with this final, kind of provocative question. Your database is now meticulously built. It's populated with data, and it's locked down tight with strict constraints and precise data types. Honestly, it's a masterpiece of organization. But how will you extract the exact stories your data is trying to tell you? How do you actually find out which branch had the most transactions last month, or which customers prefer a specific product? Building the database is really only the first step of the journey. In our next explainer, we're going to answer that exact question as we dive headfirst into the art of the SQL query. Until then, keep your data clean, keep your constraints tight, and remember, a strong foundation is absolutely everything.